Diffuse3D, wide-angle 3D photography via bilateral diffusion. We propose Diffuse3D, which employs a pre-trained diffusion model for global synthesis, while amending the model to activate depth-aware inference. We inject depth information into the denoising convolution operation with bilateral kernels. On the other hand, we propose a global local balancing approach to maximize both contextual understandings. Next, I will introduce them separately. We first initialize a trivial LDI from the RGBD inputs. In LDI, each pixel lattice contains arbitrary number of color and corresponding depth values. Next, we iteratively select subproblem from the initial LDI. Each subproblem is related to one depth edge. Then expand the synthesized regions and context regions along the edge by the flood-fill algorithm. The key of our method is to inpaint faithful image content in the occluded regions by diffusion model. For a diffusion model, its forward process is to sequentially add Gaussian noise to the input. The reverse process is to gradually remove noise and generate image. In specific, the diffusion model iteratively runs the denoising autoencoder to predict the noise. However, the convolution mechanism treats the pixels of different depths equally, resulting in synthesis content of color depth inconsistency. To relieve this concern, we present a depth-injected bilateral diffusion which leverage depth information for image inpainting. In specific, we take the kernel of convolution as the spatial kernel similar in bilateral filter. As shown in this figure, depth differences serve as the depth kernel to reweight the filter. In practice, we apply Gaussian for the depth kernel. To better model the global and local relationship for inpainting, we come up with a cross-layer inpainting strategy. We feed the context regions into the local branch and global branch separately and apply the inpainting model to each branch independently. Finally, we fuse the inpainted images into a composite image by a distance-based weighted fusion. Here are some qualitative comparisons. Our method synthesizes realistic and geometrically consistent image content. The qualitative evaluation and user study also shows our method outperforms other method. Ablation study shows all the components contribute to the final performance. Our method can achieve superior results in challenging scenarios. Our method is capable to handle depth maps from different sources, and can be applied to any diffusion model. Our incorporated bilateral weights can produce better results against traditional diffusion. Here are some demos. Thanks for your listening.